Welcome back and welcome to a new session and the last part of the semester. So what I want to do today is actually to discuss a little bit the overarching approach to project number 2 and what can be done. This is also based partly on the kind of inputs I've gotten from you guys. And the plan is then to take first a kind of more top-down view on things. And let me just do one thing here before we get started, because the okay, so the kind of idea is to try to take this kind of more top-down approach. And we are going to look at different variants of the project. And we're also going then, since I got some kind of feedback from you guys that there is an interest in looking at the generative models. And then in particular, one of the things which allows us to catch many birds with just one stone is a generative model called Boltzmann machines, or these are called energy models. So generative models is the big fashion in deep learning and machine learning and artificial intelligence. And you probably have encountered models or methods like variational autoencoders. You probably heard about diffusion model, stable diffusion, which is the hottest thing in town now, which is essentially what is the algorithmic foundation for many of the new features of ChatGPT and so on. And the Boltzmann machines is just one example of these types of generative models. And it, yeah. Okay, so actually I'm going to say something about that in just a few moments so that you see first a big view of it. Now, the thing with generative model, in a sense, a neural network, when you use that in a quantum mechanical context, is also a generative model. Then, the reason why we are thinking of using Boltzmann machines is that this allows us to actually take everything we have developed in project 1 and simply replace the trial wave function with another trial wave function. So for us, this is an extremely simple way of actually introducing machine learning and deep learning to the solution of quantum mechanical problems. Then I know that some of you would also like to study fermionic systems. So I would. Now this is Siri actually popping up here and asking questions. Okay. So the sorry for that. The alternatives which we have are this deep learning approach, and I will discuss that a little bit more in detail today, and have you to get you started. And again, we will take this more kind of top-down approach where I show you what is needed to program, and then we will try to derive the various equations which are needed gradually. We have the one with fermionic systems, which is a continuation of project 1. So that entails essentially you replacing a trial wave function with bosons with a trial wave function which has the right antisymmetry. And there is a fermionic system which is very popular nowadays in solid state physics and semiconductor physics and nanotechnologies. This is a quantum dot system. So that's also something for those of you who are interested. And then I know that there was essentially no kind of strong wishes to do Hartree-Fock theory and time-dependent theories, but I put up 2 alternative projects here, and you can take a look at them. The projects which we have, you will find them under this projects 2024, and exactly where you found project 1. And project 2 has then this 4 different variants. So the ML is the machine learning part. the VMC here is the fermionic part. And then we have a time-dependent artifact and a coupled cluster theory for those who have taken many-body physics and would be interested in applying one of the more familiar or standard many-body methods. So these are different possibilities. If you have some other things you would like to discuss, I mean, please don't hesitate to bring it up. And I can try to tailor the project to your more specific interests. That's always a possibility. But the lectures now will mainly focus on the machine learning approach together with the way you can implement a fermionic system. And that means that the only element you need to add to what you did before is to include a Slater determinant, which gives you the right anti-symmetry. And then we will have a correlated part, which is not so different from what you saw before. Now, for the machine learning project, there are several options you can follow up. So one here is to actually take project one and do a bosonic system. The system which I describe here is just a simple 2-electron case, which is pretty similar to the one which we had in project one. So these are 2 electrons in a harmonic oscillator trap, but they also interact with each other. And there is a trial wave function which you actually have encountered in those examples which I used in the lecture notes. So it's essentially that system of 2 electrons which are trapped in a harmonic oscillator trap. And this is again an example of these quantum dot systems, which are extremely popular as candidate systems for making quantum gates. And there is a lot of experimental activity going on at the Center for Material Science and Nanotechnology at the University of Oslo. So if this is something you're interested in, there's a lot of things which we can combine with a research interest towards more semiconductor physics and nanotechnology. So these are actually candidate systems, and people have made quantum gates with quantum dots in order to actually make quantum circuits. So these kind of systems are widely used, but let's go back a little bit to a kind of overarching discussion about what is a generative model. So I know that some of you have taken a course in machine learning. So a standard model like a neural network, which you may have encountered, or convolutional neural network, is normally called in the literature a discriminative model. So a discriminative model, and I'm going to illustrate this by pictures, is now you having data which are labeled. So that means that you would feed in data here, like these images. So you have paintings of Van Gogh, and then you have some other paintings which are not made by Van Gogh. And then you would simply put a label on 1 on the Van Gogh paintings and label 0 on those which are not Van Gogh paintings. Then you train a convolutional neural network on that data set. So you can have thousands of images which you train. So you can do a convolutional neural network, etc., etc. Now, what you get then, when you have trained that network, is a network with parameters which allows you to discriminate. So you see discriminative, you can then discriminate between a Van Gogh. So if I now feed to that network I have trained a painting of Van Gogh, if it has been trained properly, it should be able to produce 1, which means that it recognizes this as a Van Gogh painting. But this means that you have labeled data. Everything has been determined beforehand. So you put a label that this is Van Gogh, not Van Gogh, etc., etc. And then you can make a prediction on all this data you've been training, and then also apply the model you have trained and developed on data which was not included in the training. So this is essentially the kind of what we normally call the standard approach, which you will encounter in machine learning, where you train something and then you want to make a prediction and discriminate between different images or paintings, like in this case, which were not included in the training. Now, a generative model is different. So if you go back to a generative model, you still have training data, but now you're training a probability distribution. So you train a probability distribution on this data, but when you have trained it, then you can produce new images of, like in this case, horses. And these horses may be different, right? So you probably, if you look back, only some 5 to 10 years ago, when people used, let's say, Boltzmann machines or variational autoencoders on training, let's say, images of humans, you could have your variational autoencoder or the Boltzmann machine produce humans with 3 arms, for instance, because they were not that sophisticated. Or you could see images of people with 6 or 7 fingers, right? That was not uncommon to see. Now these models are much, much better. And for those of you who have used software like DALL-E or ChatGPT to generate new images, I mean, the quality is amazing. So what you end up, a generative model, if you take this kind of overarching view on it, is that you are now training a model based on some data, obviously, and then you get a probability distribution, and with that, you can produce new images. Now, when you translate this into quantum mechanics, in quantum mechanics, you don't need, you can actually do that with a neural network. So what happens then is that the trial wave function is replaced by a neural network. Now, since your trial wave function squared is then the neural network, you produce a probability. So in that case, even using a neural network becomes a generative model for quantum mechanical applications. Now, one of the applications or one of the methods which has been very popular is the Boltzmann machine. And a Boltzmann machine is actually you setting your trial wave function equal to a Boltzmann distribution with parameters. So that's a kind of overarching view you can take on it. So let's try to go back to the whiteboard and look at what are the kind of ingredients which we need to deal with in order to implement a Boltzmann machine. So I hope you see the kind of difference here, right? So when we are dealing with a quantum mechanical problem, in a certain sense, when you square the wave function, we have a probability. Yeah.
Does the temperature then becomes a sort of hyperparameter?
So the temperature is normally put to 1, so you just leave it out. So that means that you have a scale input in your X argument to the exponential. So it's pretty common to actually put the temperature equal to 1. So you just leave it out. However, people have, and this is something you guys can think a little bit about when you're looking at the Boltzmann machines. So you don't need, if you don't like what you did in project 1, let's say the boson system, or what I suggest, you could also look at other types of Hamiltonians. So the type of Hamiltonians which have been studied a lot are Hamiltonians like the Ising model, which some of you have encountered. You have something which is called the Heisenberg model or other type of spin-like models. So if you would like to explore those type of Hamiltonians instead of what I propose, there's a lot of flexibility in the projects here. Okay? So let's go down or dive into the whiteboard here and take a closer look at what we need to do. And then we are going to go back to the Jupyter notebook and look at the code and what needs to be implemented. So what we will look at now is essentially the following. So we're going to look at deep learning models, but we are going to look at generative models. And in our case, the energy-based model is actually going to be the Boltzmann distribution. So what we are going to do now, so let's stick with this at the kind of, stay at the kind of overarching level. And I know that most of you have actually taken a course on machine learning. So what we are going to do now is to use either, and this is something which I don't recommend in the beginning. So the first point here, you can actually let a neural network. And then I'm going to define that as NN of X. So X is now the positions of the different particles. So this is a vector. And this depends on some parameters theta, and that can be our wave function, the trial wave function. And then we have a t here for trial. So I don't recommend starting with that because that's going to be, can easily become more time consuming. So keep in mind that this course is scaled to 10 credits. And we would like to stay within that kind of workload. So a neural network, this means also that when we then square it, we have a probability, which we will call P of X of theta, which is then equal or proportional to the neural network squared. So in that sense, even if a standard neural network, the way we are used to think of it is something which is used with discriminative model, a neural network now becomes a generative model again. Because we are going to train a specific function which we want to optimize. The function which we are going to train is the energy. So we are going to calculate the expectation value of the energy, irrespective of what we do. And this energy is going to be a function of these parameters X, or these positions, and the parameters of the network. So this is the quantity we calculate, and then we want to minimize that one, which means that we are going to, again, calculate the derivative of this expectation value, as we did in the previous case. So all the optimization part, which you developed for project 1, is something which you can reuse here as well. So this is the energy of X of theta, like that. And we want to have that one equal to 0. So in principle, what we end up doing, whether we use a neural network or Boltzmann machine, is essentially to optimize the same type of equation as before. So what we end up with then is an optimization problem with the argument where the theta is now some set of parameters. They can be real, they could also be imaginary. And then we are simply going to optimize this problem here. So this looks very much like what we did earlier with the standard variational Monte Carlo, except that now your trial wave function is a neural network. Now, there is a lot of software around. So existing software is one which I recommend, and that is software. And one of these is called Netcat, and it's actually not that difficult to use. And this was developed by Carleo. So there is a famous paper. These were actually the first people to revive a lot of these kind of calculations. There is a science article, and there's a link to that in the project, a science article from 2017 with Carleo and Troyer. Yeah.
We've been doing this
So you can decide, but this library, Netcat, is actually written in Python. Now, this library contains examples of Hamiltonians, like the Ising model, the Heisenberg model. So if you would like to compare your code with what has been developed by Giuseppe Carleo and collaborators, this is something you can easily do then. So if you don't want to do the bosons or the simple 2-electron case, which I propose, you can actually replace what is in the project with similar Hamiltonians. So I want you to actually think of exploring different possibilities here. Now, so training a neural network is something which is also doable, but it's going to be more time consuming. So what I would suggest is that we replace a neural network with a Boltzmann machine. Now, a Boltzmann machine is actually a neural network, but it is a little bit simpler for us. So the NN stands for neural network with Boltzmann machines, or Boltzmann distribution. It's more correct to say it like that. So it means that we are going to have a trial wave function now. And this is something which you can also play around with. From a computational point of view, it only introduces a factor of a half. So you don't need to think that much, but it's pretty common to actually replace the square root of, or not the square root, but the absolute value of the wave function, or the probability of the quantum mechanical probability with the Boltzmann distribution. So we would typically replace that one, beta, and then we have the parameters x of theta, and this is divided by the partition function. So let's just leave that one out just for the moment. So this is the Boltzmann distribution as you see it here. So that means that your trial wave function is now a Boltzmann distribution. And then the model itself comes through the way we are going to describe this energy. And this is why a Boltzmann machine is called an energy-based model. Now, there are many other reasons for why I want to introduce the Boltzmann machines. It's one, because basically all of you are physicists, and it means that we are pretty familiar with a Boltzmann machine. We have with a Boltzmann distribution. We have a kind of intuition about it. It's common to put this beta equal to 1. So that means that the energy which you see here is not a quantum mechanical energy. So this can be a little bit confusing. So this energy is given by a model. So this E, and let's just give examples of that. So this is not the energy of the system. Actually, this E is a function of x and some hidden variables, so which gives us more flexibility in optimizing the problem. So this is equal, so we have several cases. One, and if you're dealing with spin systems, where the spins can take values like -1 and +1, so then binary values, it's common to use what's called a binary Boltzmann machine. In that case, the way this is going to look like, so I'm just going to present the expressions here, and then we are going to look at the details and how we are going to run calculations. So we have as a function of theta, and this is given by a function where we now sum over the visible layers. So that is something which I will put with a V. I'm coming back to what that is. There is a parameter A. This is multiplied with x of I, plus a new parameter, and this is sums up to the number of hidden nodes. So this, I'm going to put a V here, so that is the visible nodes, and these are the hidden nodes. So let me just put that one, visible nodes. And these are called the hidden nodes. So this has a parameter bj times h of j, plus, and there's a term now which runs over both of them, of v of n, of h of n, and then there is a weight constant, wij, and then this is multiplied with x of I and multiplied with h of j. So this is just a model which we are setting up. So what does this look like when we are looking at a neural network now? So let's take a closer look at the neural network for a Boltzmann machine. So what you would have then, so if we now set up the neural network, what we have is a set of visible nodes. So we would have x1, x2, up to this x of vn, the last one. Then we have the hidden nodes. So these are the visible nodes. So if you have two particles in two dimensions, you need 4 nodes. The X and Y values for particle 1 and the X and Y values for particle 2. Just to give you an example. So if N is equal to 2 particles in 2 dimensions, then you have that V of N is equal to 4. This is like you having an image. If you have 100 pixels, you have 100 input nodes for a neural network when you want to train on images. Here, we are taking the input variables, I mean the positions of the particles, which then enter the setup of the Boltzmann machine. Then we have the hidden nodes, and they can be as many as you want. So these are just parameters. So these are the hidden nodes. And in that case, we have an H1, an H2, and this goes all the way up to H of N here, the number of hidden nodes. So these are parameters. And then they have their own bias value. So these parameters AI and B of I, B of J, they are called the biases. And this is to hinder that the training of the network stops by accident in case the weights are different or equal to 0. So these are, and then we have Wij. These are normally called the weights. So these are the parameters which are then included in this common denominator, which we called theta. So theta contains now a set of biases and a set of weights which we need to optimize. So the optimization problem now is also actually setting up an expression for the total energy. And then this total energy of the system with exactly the same kind of equations we had before. We need the local energy. We need the gradients of the expectation value of the energy as you did in project 1, because you're going to optimize everything here. Now, these nodes are typically connected then. So, and these are connected with these weights. So this would be W11, here I would have W12, etc. So all these are connected. Now, there is no connection within the layer. You can, if you want to, you can make these Boltzmann machines more complicated. So you could have more hidden layers. But by experience, what one has seen is that this often makes the training more complicated. So a typical Boltzmann machine, which you see here, what you see now is called a reduced Boltzmann machine. No, sorry, not reduced, restricted Boltzmann machine. So you would normally see this as being shortened as an RBM. So this is your network. So if you think back to a standard neural network where you do your feed forward and back propagation part, you would do exactly the same here. So it means that the training which we are going to do is a training where we will optimize the total energy of the system, which is this quantity. And here I've actually put in E, and this E is not the same as this energy here. So we should actually distinguish them a little bit. So let's call this an E tilde, because that's not the energy of the, or the Hamiltonian of the system which you are looking at. So let's put a tilde here just to make this distinction. So this is your model. And that model has parameters to be trained. Now, in this particular case, when you have a binary model, like we are having here, for the binary model, what you have in that case is that xi's, they take binary values. So that could be -1 or 0 and 1. And same with the hidden parameters. They could take values -1 and 1. Okay. So what we are going to calculate the derivative of now is a trial wave function, which is given by a Boltzmann machine. Now, since we are looking at the variables for the input, which are continuous variables, then a binary machine is normally not the best choice. And what is normally done then is to have a Gaussian binary or a Gaussian Boltzmann machine. Now, what we need to introduce also are some technicalities from statistics about marginal probabilities and conditional probabilities. So I just wanted to remind you a little bit about these technicalities as well, but we are going to say that a little bit more about that later. So the idea first now is to give you the kind of overarching view of what we are doing. So instead of you having a trial wave function, where the trial wave function is given by the physics, which we think is relevant for that specific system, we are now replacing the physics motivated trial wave function with something which is given by a neural network. So whether you use a Boltzmann machine or you use a standard neural network, this is something which is a matter of exploration and is actually an active research field nowadays. The reason why I've made this optional is that this is something which can be more time consuming. Technically, it's not that complicated, but it can easily lead to more error searching and a little bit more complicated implementations. But this is something which I will also leave up to you, depending on how fast you actually solve this problem here. But in the project, what we have defined is essentially a project where we define a Boltzmann machine and we play around with that. Now, this binary model, which you see here, is ideal if you're looking at a spin system, like the Heisenberg model or the Ising model or similar models from statistical mechanics and solid state physics, condensed matter physics. So the binary case is something, and then in that case, you could have something, let's say 100 spins. And if you have 100 spins, you have 100 input nodes. And they take only values -1 and +1. You would have activation functions for the hidden layers and the visible layers. And these activation functions can be a sigmoid function or similar functions which you have seen before. Any questions so far? So I'm trying to give you the kind of bird's eye view on what we are going to look at. So let me just remind myself of what I wanted to say a little bit about. That one. Okay, so let us just look a little bit first at the basics of the Boltzmann machines. There is for the project, what we can do, and which I would suggest to do, is actually, instead of having a binary, so we have this 2 here, case 2, which is a Gaussian binary. And for the Gaussian binary, what you would have then is an energy model. So this is this E tilde of X with the hidden layers of theta, which is then given by a sum from I equal 1 up to V visible. And in that case, we are taking an X of I minus an A of I squared. You can have a parameter here if you want to, which is the variance of these X's. So this looks very much like something coming from a Gaussian distribution. And if you're thinking of the harmonic oscillator, because when you exponentiate this one, it looks like the Gaussian distribution. And if you're thinking of the harmonic oscillator, this is something which is actually pretty good for modeling a harmonic oscillator wave function. So if you think back, because this comes within as an exponential, and if you look at your Boltzmann machine, you're going to have e to the minus this energy model. So that means that the parameters which you choose here, or this kind of this Gaussian binary model, means that you have something which looks pretty much like a harmonic oscillator wave function. And if you use that one, you will see that for the non-interacting case, you're going to be spot on the exact energies. And then you can have a binary case for the hidden layers. You could have a continuous one as well, but that makes the equations to optimize a little bit more complicated. So we are going to go through the details of all these equations here. So we would have a j equal 1 up to the hidden layers. And then we have an b of j of h of j. So this is the binary part. And then we have the so-called interaction part, or the interacting piece. It's not a real interaction, but it gives you a coupling between the hidden layers and the visible layer. So think of these h's as additional parameters in your optimization. And in this specific case, if we are dealing with spin systems, then you know that this could actually be a viable way to add some extra degrees of freedom. Now, in Monte Carlo calculations, people have used similar techniques back in the 70s. There is actually a guy called Carlos who essentially did the first diffusion Monte Carlo calculation, who called this for a shadow wave function. So what you had was a wave function with additional degrees of freedom, which you then integrate away. So now comes an important technicality, which we need to say something about. So if you go back to the Boltzmann distribution itself, so we are now having a distribution, and these are technicalities which we need to discuss a little bit. So we have a distribution which depends on P, on X, and H, and theta. And we have defined this one to be given by E of minus beta. We normally put beta equal to 1. And then we have this energy model, an X of H of theta. And then we have a normalization constant, which is a partition function. So this quantity which you see here is a quantity Z, which now is equal to, and this depends a little bit on what kind of distribution we have. So if it's a continuous distribution, we would have an integral over X. So these are multidimensional integrals of dH of E to the minus beta of E of X of H of theta. Okay, so that is your partition function. Alternatively, if it's a discrete one, you would sum over all the possible values of X. So we would have an X which belongs to a specific domain, and then you have the H's, and then you have a summation over E to the minus B. So we have an Xi and Hj, and then we have an E of Xi of Hj as a function of theta. Now, when we are looking at the quantum mechanical object we are interested in, we don't want a dependence on H. So what we want is actually a wave function, a trial wave function, which depends only on X and these parameters theta. So what we want then is P of X as a function of theta. This in statistics is called the marginal distribution, because we are summing away or integrating away one of the variables. So this is normally called marginal distribution. And in our case, So that means that this Px of theta is then given by the summation over the h of i's, or h of j's, of p. Now we can put a p of x of I here, because we're looking at a specific event. So we are summing away all these quantities which you see here. That is called the marginal distribution. Now, you will see now that in the explicit derivations of what we are needing, so the wave function at the end, we are going to integrate away the hidden degrees of freedom, because what we have at the end is something which depends on the position of the particles, right? So in the optimization, we are then going to simply produce this quantity here at the end, and then this will be a wave function which depends on the optimal parameters. Okay? So I'm still staying with this kind of more top-down view on it, so that you see why some of these technicalities come into play. So one of the things I wanted to do right before we take a small break is to remind you quickly of some of these technicalities from statistics. So, and this is just a quick reminder about Bayes' theorem and marginal and conditional probabilities. So this is just a quick reminder on statistics, which you may have seen in different courses. So if you have two domains of events, this uppercase letter X and Y, you can then produce likelihoods. Often we do assume that these are independent and identically distributed ones. So you can produce likelihoods for this P of X and P of Y. They could be the same if these are identically distributed. They don't need to be the same. So what you typically have then, if you go into any textbook in statistics, one of the first things you encounter are these definitions. And one of these is the union of events, which is then written like this. And this is a disunion. And this is typically written like P of X plus P of Y minus this quantity. And then there is a famous rule, the product rule, which simply says that the union of these guys is then given by this quantity written like this, which is the probability of X given Y, this is the vertical bar, multiplied with the probability of Y. And this is exactly the same as the other one. The probability of Y given X multiplied with the probability of X. And these are typically some of these fundamental axioms which you encounter in any course in statistics. And then, if these are independent events, as we have gotten used to in case we have no interactions, then it's simply the product of the two guys. Okay? Then, one of the quantities which we are going to use, because at the end, in our case, this X could be the positions of the particles, and Y is this additional degree of freedom we have in the optimization, which defines a neural network. So a neural network is a very flexible object which allows us to optimize a problem with additional degrees of freedom. And hopefully that one gives us a better optimization. And then you would now sum away or integrate away, if these are continuous probabilities, you simply sum away one of the degrees of freedom. And this is called the marginal probability. And you see now that this can be rewritten as the probability of X given this Y of I multiplied with that probability, where we simply use the product rule here. Then you have the conditional probability. So we assume that P of Y is larger than 0. And then you can always rewrite this one in terms of the product rule divided by this marginal probability. So these are quantities which we are going to use. And then you have probably seen Bayes' theorem, which is the same as in statistics, plays the same role as Pythagoras in geometry. And in that case, we simply combine the product rule with the marginal and conditional probabilities. And then you get the probability of finding Y, which is called the posterior probability, which is now given by a likelihood times this prior probability, which is often a model for what you as how we assume the data distributed. And this denominator plays the role of a normalization factor. So this will be the probability of x given this y, which you would get from Bayes' theorem. But the quantities which we are going to play around with are actually the marginal probabilities, but we will also need these conditional probabilities. Because at the end, we want to have a wave function which does not depend on these hidden parameters. So the marginal probability becomes a very important quantity. And you will see why these Boltzmann machines, from this expression of the marginal probability, why the Boltzmann machines are not that interesting anymore. And that's essentially because when you look at the types of models like Gaussian, Gaussian binary, with a Gaussian binary and a binary, you can find a nice analytical expression for the marginal probability. The same with a Gaussian binary. There's a little bit more labor, and you will see these expressions in the lecture notes. And if you do a Gaussian, it's getting a little bit more complicated, but it's still doable. But if you want to expand that energy model to more complicated ansatz, then your marginal probability has to be evaluated numerically. And that slows down the implementation of the Boltzmann machine. So Boltzmann machines are very attractive, but they also have a limit in the sense that some of the quantities you need to deal with, they have to be evaluated numerically, and that slows down everything immediately. So Boltzmann machines were actually, before CNNs, convolution neural networks, really wiped away all competition. Boltzmann machines were actually very popular as generative models for imaging, for classification of images. And if you go back in the literature, you will see that around 2010, which is often seen as the divide between the pre-deep learning revolution and the deep learning revolution, you will see that many people actually were trying to implement Boltzmann machine for image classification. But then the CNNs just wiped away all competition, and they simply rule the ground. And nowadays we have other and better generative models. But for us, in Project 2, this is one of the main reasons why I would like to suggest starting with Boltzmann machines. This is the item or the method which allows us to simply take what we had in Project 1 and make simple replacements. So the kind of hassle which you have to suffer, I mean, in implementations is actually, hopefully, the threshold for getting something reasonable within the next weeks should be pretty low, hopefully. We never know. So we had one group who thought they were ready, they had implemented it within a week, and then they had some results which were a little bit strange. And that had to do with two indices which they had interchanged, and it took them 3 weeks to find out. So we never know. I mean, the implementation may sound easy, but then we always end up with some stupid errors. I do that all the time. So what we're going to look now, based on this kind of a quick reminder about marginal probabilities, conditional probabilities, and other things, let's now look into what we need to program. And if we now look at what we did in Project 1, so let's quickly remind ourselves about that. Because this machinery which you developed in Project 1 is something which you're just going to reuse again in this project as well. So the thing is that we have now a function, a probability distribution of H and these parameters theta, which are given by E to the minus. And now we are now going to skip the inverse temperature. So we just put that one to 1. So we have this energy E tilde of X of H of theta. And this is divided by a normalization constant. Now, as we saw in project number 1, when we did the metropolis test and in all calculations, since we often look at ratios between wave functions, the normalization constant disappears. So the, the computationally tricky part in all these calculations, and if you go into the theory of Boltzmann machines and implementation of Boltzmann machines, they deal with the optimization problem, which also involves the partition function or the normalization constant. So a standard Boltzmann machine, so this is a small digression before we go into what we need to do. A standard Boltzmann machine optimizes this probability. This is different from what we are going to do. So in a generative model, when you are setting them up, you're actually calculating either the minimum or the maximum of this quantity. This quantity is normally given by the product of all the individual probabilities. So in a standard Boltzmann machine implementation, what you would have would be something which looks like this, and that would have a probability over all these visible guys, and that would contain a probability now which depends on all the small x's and the hi's. So this will be from 1 up to the v of n. There will be a probability of j equal 1 up to h of n, and then you would have a p of x of I, h of j of theta. At the end, you would sum up all the h's, because at the end, you would like to have a probability which only depends on this one. So if you look at these individual probabilities, what you normally do then is that you have a optimization problem where you take an argmax of the parameters theta of some dimension p, but then you would take log of this p. Normally, you also sum away h, so you only have p of x as a function of theta. So that means that in order to find the optimal parameters, you maximize this quantity. When you deal with a standard Boltzmann machine then, what you have to deal with is this quantity as well. When we do a variational Monte Carlo calculation for quantum mechanical systems, as you saw from project 1, the normalization factor is something which we don't need to deal with. And the normalization factor is actually the evil thing in all of these calculations. And if you have like atomic neon, or if you look at project 1, where you have 500 particles in 3 dimensions, then the integral behind C would be a 1500 dimensional integral. So this is typically a quantity you want to avoid to calculate. Now for us, life is a little bit simpler because we are actually going to minimize the energy. So this is what we want to minimize. E, and that's the expectation value of the energy, which now depends only on x and theta. So we have integrated or summed away the hidden nodes. This, as I said, becomes a degree of freedom, which now simply adds to the flexibility of the model which we have. So we would typically then perform an integration of this type here, but we would integrate away over p of x of theta, and then we have the local energy. Okay, this is essentially what we did. This is basically the same as we did in project number 1. And let me see what we end up with in this optimization. We have a d of theta and that is equal, as we saw before, into that leads to a, we want, sorry, not that one. We want this to be 0. And that gave us a D of the expectation value of the energy. And now I'm skipping the parameters, theta and x. For a given one of these parameters, we had this expression, which was then given by the expectation value of the local energy with 1 divided by psi, and then d psi, the trial wave function. And the trial wave function is in our case a Boltzmann machine. Minus, and then we had the expectation value of the energy multiplied with the expectation value of 1 over psi t of d of psi t of d theta of I. So this is the expression which we derived in connection with project number 1. And we are going to use the same machinery. So we need to evaluate these 3 integrals as well. Now, in our case then, just to remind you of some of the quantities which we have. So this quantity which you see here is something which we can rewrite in terms of the logarithm of the trial wave function. So this quantity here is 1 over psi of t of d of psi of t, the trial wave of d theta of I, one of the parameters. And these parameters are now the weights and the biases of a neural network. The machinery which you see here would be the same if you implement a neural network instead of a Boltzmann machine. So there's no difference in the type of equations which you have to optimize. So this will be a psi of t and then d of theta of I. And in our case, what we need to also pay attention to is the fact that this probability is now given by the Boltzmann distribution. So the quantity which we will look at, this function E, as a function of x and h and theta, is going to be a Gaussian binary Boltzmann machine. So I'm going to give you the equations, and then we're going to look at what we need to do from a computational point of view. And then next week, we are going to look at more details behind the derivations of these equations. So we are going to use a Gaussian binary. You could use a Gaussian. A Gaussian binary is ideal here for harmonic oscillator type of problems. So this is going to be given by a sum over I equal 1 up to the visible nodes. And then we have a x of I minus a of I. A of I is now the parameter, so which is part of the optimization problem. And it's common to have a variance here, but normally we would put that one to 1. We just leave it out. So take the A of I, this is a parameter. And then we have the remaining part of the Boltzmann machine, or the energy which we are plugging in. And what we would have next is plus, and then we have the hidden layers. And here we have a parameter b of j times h of j. So this is again a parameter. And finally, we have plus the sum over I and j, and then we have wij, and then we have h of j and x of I. And this goes up to v of n and h of n. And these are also parameters which need now to be optimized. And as I said, if we have, let's say, 10 particles in 3 dimensions, then the number of visible nodes would be 30, 10 times 3. If you have 2 particles in 2 dimensions, you need 4 visible nodes. And then you can decide how many hidden nodes you want to have. This becomes just a parameter, and then you can test the network and the results which you get as a function of the number of hidden nodes. Now, what we are going to assume now is that the wave function, so we can assume that the trial wave function psi of t of x of theta, so we are not interested as a trial wave function as a function of the hidden variables. So that is going to be equal to, and now we can decide whether we want to square the quantity or not. So we could think of this as the wave function squared, or we could have the wave function to be either the probability, the Boltzmann probability, which is an E of minus this E tilde of x of theta divided by the partition function, or we could simply say that the trial wave function of x of j of t is actually equal. So this is a distribution of p of x of theta, or we could simply say that this is equal to the square root of p of x of theta. So these are just different options. And the only thing which happens then is that you're going to get, when you take the log, you just get, since you're taking the log of this trial wave function, you just get a factor of 1/2, right? So suppose now that we take this approach here, okay? That means that your trial wave function is simply going to be given by 1 over the square root of z. And then I have the square root now of, and so let's just put up this trial wave function. So this will be the square root of a sum over all the hj's. I'm going to write it like this. And then we have e to the minus e, because we need to sum up over all the hidden nodes. And keep in mind that these hj's, they take now as a binary case, they can take values of -1 and +1. Or often simpler, 0 and 1. This is up to you to decide what kind of values they should take. So what we need to do then, when we now take this trial wave function, what we get is the following. So we need to take the log of that wave function. We take ln psi of t of this function x of theta, and that is going to be given by -1/2 of ln of z. And now when we are taking the derivatives here, the thing which is nice is that c is actually a constant. So we can normally omit that one in the calculations of the derivatives. So because we assume that this is just a normalization constant. So we have an I equal 1, and then we're going to have up to the sum of the visible nodes. So we will get an x of I minus a of I, and this is squared. And I'm just taking away that factor of sigma I squared. And then I have plus 1/2, and then I have a j equal 1 up to the parameter v of h. And this is going to be given by ln of 1 plus e, and let's see if I'm doing this correctly, plus of I equal 1, and then I have a v of n here, and then I have x of I wij. So the quantities which I need in the calculation in the optimization, so in the optimization, we need the following objects. We need a d of ln, and then a psi of t with respect to this quantity ai. We are going to need the derivative with respect to the parameters b of j. And finally, we also need the derivatives with respect to the weights, Wij. So we need to set up the expressions for these quantities. Then, and these expressions are in the slides, so I'm going to point to you where you have all these expressions. It's not a very interesting exercise to do, because you have to perform these summations. And you see quickly why going beyond a Gaussian binary or Gaussian is going to give you more and more complicated expressions here. Now, with a Gaussian binary and a binary and Gaussian, you can find analytical expressions for these quantities which we need to evaluate. And in the lecture notes, you will find all these derivations. I'm going to point them to you, but what I want to do now is more to show you what we need to implement. So these kind of derivatives, you will find the explicit analytical expressions in the lecture notes. I will come back to some of them next week. But what we need then, when we now look at the local energy, this is another quantity which we need to set up. This is the same as 1 over psi of t times h times psi of t. And when I'm using my trial wave function, what I will get then is something which is going to look like as follows. I will get a factor over half, and have I equal 1 up to the number of particles which we have. And this is going to be given by minus, and then I add dln of psi of t. And now I need to set up, this is the local energy, the derivative with respect to the x's, the positions. So I'm just giving you the final expressions, minus. So this is a calculation of the local energy with that specific trial wave function, ln psi of t. And then since I have the harmonic oscillator, I need a harmonic oscillator frequency, and then I have an Ri squared here. And just to remind you of the type of problem which we are having, is that this Hamiltonian is going to be given by I equal 1 up to the number of particles, and then I have minus 1/2 of delta I plus 1/2 of harmonic oscillator frequency times Ri squared. And then I have plus a sum over I less than j, and this is the interaction piece. So this is going to be the local energy part, which I need to include in my calculations. And, oh, by the way, I think I forgot, there is an additional term here. Actually, I should sneak that in here. This was missing. There is plus a sum over I less than j of v of Rij. Sorry for that, I just forgot that one. So these are the expressions which we need to calculate. So we need explicitly to now set in the Boltzmann machine and calculate this expression here. We would need this expression here. These expressions which you see here, these are much simpler. This one is pretty simple because it doesn't do anything on the wave function. So you just multiply with the trial wave function and divide with the trial wave function. And the same with the two-body energy, because that gets multiplied with psi of t, and then you divide with psi of t here. So this term is pretty easy. This term here is pretty easy. But then we need to actually set this one up and this one up. In addition, in the optimization process, when we are calculating the derivatives of the energy, we need now this quantity, we need that one, and we also need this quantity here. So let me show to you in the Jupyter notebook for this week, and then next week we will come back and look at some of these expressions and go through some of the details if you feel an excitement around that. It's not that exciting actually. It's a pretty boring exercise, but I was planning to do that more for the sake of completeness. So let's take a look at the kind of expressions we would need to calculate. And you will see if you scroll down here, the different types of the Boltzmann machines which you can implement. And in here, what I've done is actually to calculate these different probabilities. So this would be if you take this Boltzmann machine, you have this as a marginal probability. And you can go through these calculations if you have a continuous variable d of h. Actually, d of h is not continuous, it's discrete. And then you can actually find analytical expressions for these quantities. So if you scroll down, it's perhaps the not most exciting thing to do, but we will need, for the Gaussian binary, we need to set up the marginal probabilities, and we can sum up the partition function in that case. We will need the marginal probabilities, so we are summing up of all the hidden nodes. But let's scroll down a little bit and just look at what we need to implement. So when people introduced these Boltzmann machines in the first time, they looked at both the possibility that the wave function squared is given by the Boltzmann distribution, but also the fact that you would put up the wave function, like in this case, and that means that this would be the square root of that quantity. So these are different approaches. The only difference you get is a factor of 1/2. So one of the things which we looked at was actually this quantity here. And then you can set everything up, and you will find when you go through the algebra, you will find an expression for the wave function itself, which you then plug into the calculation of the cost function. So this is essentially what we are calculating as a function of all these quantities. And this is what I put up in the slides. So this is a quantity which you would need to evaluate, the log of this trial wave function. And then we have these different derivatives. So what I'm doing here is just to provide the analytical expressions which you get. So if you move beyond a Gaussian Boltzmann machine or Gaussian binary, these equations get much more involved. And in some cases, you would end up having to evaluate them numerically, which is something which will definitely slow down all the calculations. And what you see here are the cases if we take the wave function either as the probability or if we take it as the square root of the probability. And then you simply just get a factor of 1/2 in difference because you're taking the logarithm. And you know the logarithm of square root gives you the function times the log of the function times a factor of 1/2. And these are the quantities which you get. And then you plug in the equation for the energy. And then we have the local energies and the way it's going to look like. This is exactly the same quantity which I put up. So all the derivations which I gave you on the whiteboard here, they are listed in the Jupyter notebook in more detail. I don't know how excited you are or how disappointed you would be if I don't go through all these calculations, but I'm going to show you some of them next week. But this is not the essential thing. So hopefully I've done the derivations correctly because I put in all the analytical expressions for the derivatives which need to be set up. And then you would find the same equations. And then there's a Python code here. So this Python code is now done for the case in project 1 for electrons, which are not interacting. But you can add the interaction piece as well. So in this specific case, I'm now setting up the trial wave functions, as you can see here, and I'm plugging in those expressions which you saw in the above here. And now I'm simply setting up a loop over the number of particles, the dimensions here, and I also need to include the hidden nodes. So these become additional parameters. So the trial wave function now is a little bit different from what you've seen before. And then the local energy takes also as a sum over the number of hidden parameters. So all these equations which you see here are the equations which you would implement for these cases here, and with a local energy which does not include the two-body interaction. You can include it if you want to, but now it just has the harmonic oscillator in the cases which I will run now. So it means in principle that when you've done with these specific applications of a new trial wave function, it means that essentially what we have is the same type of machinery as before. There is actually an if statement. I can add the interaction if I want to. And here I have the analytical equation for the derivatives. You recognize the quantum force. This factor here is the factor which is in front of these wave functions, which now includes the hidden parameters. And then I have the energy minimization. And here I'm just running these same parameters as before. I have included importance sampling. I'm calculating the derivatives of the trial wave functions, etc. And then I have my quantum force as before. This is my metropolis testing, which is the same as before, as you can see. So the main difference is actually, it resides in the calculation of the derivatives and in the local energy and trial wave function with this new expression for the wave function. So if you now look at this non-interacting case, this is now given by two particles. I'm now introducing the dimension, so that means I will have 4 visible nodes. And then I also decide to have 2 hidden nodes. So you can change this. This becomes just as a parameter. And then I'm initializing the parameters with random numbers. So these are the weights and the biases. And then I calculate the energy derivatives. And you see here I have a brute force gradient descent. The big difference now is that I need the gradients of the parameters A, the gradients of the parameters B, and the gradients of the parameters W. So this is a change from what you'd had previously, where you had the variational parameters in the wave function. Now the parameters which you have, it's still a variational calculation. The parameters we have are the parameters of a network. So if you were to replace the Boltzmann machine with a neural network, it would be, you would actually have to calculate these derivatives numerically. So with the Boltzmann machines, you have actually, with a Gaussian binary one, you have analytical expressions for all the derivatives. But it gives you less flexibility than in case you run this with a standard neural network. The iterative machinery, the function you want to optimize, is still the energy. So that means that the derivatives you need, if you were to do this for a neural network, so the same parameters would be needed here. I have an eta parameter, which I'm setting to 10 to the minus 1, 10 to the minus 3. And then I iterate, and you see now I do 50 iterations in a very brute force way. I don't have a stopping criterion. And then you will see now that the answer, harmonic oscillator in 2 dimensions, no interactions, oscillator frequency to 1, the exact answer should be 2. And you see now that this is getting spot on. Why didn't? Okay, I just rerun it. Yeah, okay. I had some small things here which I didn't update. But you see, this is doing a pretty decent job. So if you take the bosonic case from project number 1, you could actually run that case with a Boltzmann machine for as many particles as you want. And that is also a useful test. But the thing is now that you have analytical expressions for all the derivatives, depending on the type of energy models which you end up with. So the trade-off here is that it's a pretty nice model. It works well when you have this kind of Gaussian type of wave functions. If you don't have that, what you will see is that the solution will not be that good. So you can see now a case here compared to what we had before. So what I'm going to do now is to add the interaction. So if I add the interaction, which is given by the Coulomb repulsion between two electrons in this specific case, the exact answer for two electrons in two dimensions is 3. What you will see now is that this trial wave function is not optimal, and I'm not going to get 3. I will get something which is 3.2 something, and it will keep oscillating here. I also have very few hidden layers, so which gives less flexibility. So one thing which people often do then is to take this trial wave function and multiply it with the same kind of factor, adjuster factor, which we had in the examples before the Easter break. So you will take a Boltzmann machine, which has some flexibility to find optimal parameters, and you can multiply that with some basic physics information about what the correlated part of the wave function should look like. So a Boltzmann machine, the way it's set up here and the way it normally is used, gives you less flexibility. However, as I mentioned, if you don't want to look at this problem with, let's say, interacting bosons or electrons in an oscillator trap, you can replace the Gaussian binary with a binary and have as a Hamiltonian either the Ising model or the Heisenberg model. So these are options if you want to change what we have proposed in the project text as Hamiltonian models. In that case, what you will see is that a binary Gaussian model, a binary Boltzmann machine, gives you very good results for the exact energies. But you will see that in this case, and this is calculation which I made, which is pretty simple, it doesn't seem to be converging properly to a value here. It just fluctuates quite a lot. I don't have that many Monte Carlo cycles as well. So if you want to get closer to 3, you would have to add more physics information to the trial wave function. So the Boltzmann machine here, the way we set it up, a Gaussian binary one, that's the energy model for the Boltzmann machine, is not able to capture all the relevant physics. Whereas for the non-interacting case, we were basically spot on the exact energy. So I'm going to stop the recording here. And I invite you to take a look at these equations, look at the projects as well, the different projects. We will discuss this in more detail next week. And then we will also look at the implementation of a Slater determinant for those of you who may be interested in looking at an extension of project 1 with fermions instead of bosons. And then we will also look at next week at other types of Hamiltonians which can be implemented with a Boltzmann machine, like the Heisenberg model or the Ising model, in case you would like to study those systems.